So we've got through some of the theory of pipelining. Now we're going to actually build it up. And this assumes that you've had a look at some of the other videos where we build some of these pieces of hardware and then see how we can put them together. So we're going to pipeline in the 4-stage hardware in these 3 separate pieces. First thing we're going to do is have the fetch unit. That fetch unit is just the program counter, addresses the instruction memory, and puts the result in the instruction register. Super simple. We have a little +4 there that is the increment for the program counter so that we can have it sort of ticking one after the other. But that's really all there is to it. That's going to be all that happens when you fetch an instruction. We're just going to address the instruction memory and put the result in the instruction register. And then we're done. And the whole point of pipelining is that that has to operate independently. So once we're done, we just let the instruction carry on, and we have to assume that the other parts of the pipeline will do their job. So what are the other parts of the pipeline? The read is where we get the operands from the register file. So the instruction register contains the address of the source registers, right? Which registers we're going to use, 2 source registers, source 1 and source 2. And then we put those register identifiers into the register file, and out comes the actual values from the register file. But again, we just store those in the flip-flop that is between pipeline stages, and we assume that the rest of the pipeline does its job. So in the read portion, we have to assume the instruction register contains the information we need, and then we have to put the information that we read from the register file into the latch between pipeline stages and carry on. So that's stage 2. Stage 3 is execute. We're going to take those values that were read from the register file, and again, when we're executing, we just assume those are the correct values, that somebody else has done their job, and then we present them to the ALU and store the result into our latch, the pipeline latch after the ALU. So the ALU, all it has is registers before, registers after, and we assume it does its job. These are developed one at a time separately, but let's see what they look like when we put them all together. So because the instruction register at the end of the fetch stage is the same latch as at the beginning of the read stage, that just comes together. Because the ALU source latch is the same latch as the output of the register file, those come together, right? So now we've got source addresses and source operands in the register file. We've got flip-flops or latches for the sources for the ALU and the result R from the ALU. But that gives us a result. Now we got to decide where to put that. We got to put that back in the register file. And this is the part that often gets people confused when we're building a pipeline machine isn't the register file already working? Isn't this already some kind of a problem that the register file is used both when we're reading and when we're writing? Well, the key to remember here is that when we're reading, we're only ever pulling information out of the register file. And when we write, we only put information into the register file. So we can separate those two conceptually, that in stage 2 of the pipeline, we're pulling information out, and in stage 4, we're putting information back in. So because those are really different operations, they don't really collide. And we call this the write back stage. Looks like this. I added more complexity here. I'll come back to the control logic in a second. But the write back stage, you can see the idea is the result from the ALU gets written back into the register file. And so really now we have 4 stages of the pipeline. We have the fetch, we have the read, we have the execute, and then the write back looks like that. But let's go back in time and think about the way we're actually going to be able to control this pipeline. Because just saying that the instruction register presents to the register file and that the register file presents to the ALU through these pipeline latches, that's fine, but how does the ALU know what to do, right? Well, the instruction register contains the control logic or the control information for what should happen at the rest of the pipeline. So that means we need to carry it along with us, right? Because each stage is independent, for each stage to know what it's supposed to do with that instruction, we have to have the recipe come along with us, right? If we're in a restaurant, we can say I'm going to cut onions, and the onions are the same for every single dish. Or if I have to cut onions differently for every dish, then if I'm the onion station, I have to know what dishes are coming down the pike. So I can say, okay, I need a dice here, I need this here, I need this here. We have to carry that recipe along with us as we go, right? So that control logic has to be carried with us, and then that allows the ALU to know what it's supposed to do as it's operating. So in this example, we're going to add control logic as well as write back. So not only are we going to add a wire that goes from the ALU result back into the register file, we're also going to add a wire that takes the opcode from the instruction register, which is missing right now. And we're going to add that, and we're going to carry it along with us. How do we carry it? Well, we've got to put it in those intermediate latches, right? Because that's the only place where information moves from one pipeline stage to the other. Anything we want to be able to present to the execute stage, we have to put in the latch between the read stage and the execute stage. So it looks like this. And yeah, that's a lot to add. But what we've added here is two things. The opcode here that's going to carry along and tell the ALU what to do. We've also added the destination address because when you think about it, if we have an instruction go all the way through the pipeline, the ALU produces a result and writes that back into the register file, where do we write it back? We need to know which register to put the result in. And so we have to carry that information along with us as well. Any information that we need in order to execute that particular instruction at that particular stage of the pipeline, we have to carry along with us in those intermediate latches. So that's the idea with this stuff. There's a couple of little tweaks that we have to add here to make this actually functional. And one thing is to recognize that sometimes we get information from the register file, but sometimes we get information from the instruction itself, right? If we're doing a literal add, right? Add one to a register rather than add a register to a register, that information is in the instruction register. But if we don't do anything about it, it's going to get lost. So we have to carry that information along and then provide an option for the ALU to be able to choose that information. So that looks like this. Here's the old one, and here's the new one. So we're going to add some logic that allows us to choose between a register and a literal value, but we have to carry that literal value along, right? That's here. The literal value, which again is part of the instruction register still, that gets carried through, and then we can sign extend it and put it as an option for the ALU. We've added another thing here. I'm sort of doing all things at once, which is can be a little bit confusing. Plus I'm sort of in the way here, but you'll see. The other thing we do is allow the ALU to calculate the next address if we're going to be branching or jumping. And how do we do that? Well, we need the program counter, right? We need the program counter, and we need whatever we're adding to. So program counter plus some offset to get us branching back or forward in our code, whatever. That's going to be how we calculate the next address. So that means our program counter has to march along with us, right? And that means that we then do some math to the program counter and put it back in place. Now this is going to get problematic because the ALU, maybe we want to use that to make a choice, but we also have to use that to calculate the new value of the program counter. So let's look at what it looks like first. This is what it looks like. So the program counter gets presented to the ALU, but we're sort of skipping these registers, aren't we? Isn't that interesting? The program counter gets presented directly to the ALU rather than going through these registers. Now, why would we do that? Well, because when we do a branch, we actually want the program counter value itself, not the program counter value 2 instructions ago. When we talk about branches and pipelines, we will get into some of the complexity of we got to make a decision, we got to take a branch, take a not branch, right? Go to a different instruction stream, but we have already started to execute some instructions. There's a lot of really weird stuff that happens once we do that. The point is here that we're adding a channel that allows the program counter value here to be presented to the ALU in addition to the other options we've already got, which is the literal from the last pipeline stage, or the register file values from the last pipeline stage. So this is now getting close to our completed machine, but we're missing one thing, which is we don't have any way to load or store information. There's no data memory here. So to add the data memory, this is the last little chunk. We are going to use the ALU address as the ALU output as the address for the data memory. Now, why do we do that? Because that allows us to do our interesting addressing modes, right? We can take a register and we can add another register to it to make an indexed address, and then that gets presented to data memory and then used to load or store whatever. So this is what this looks like. Here's our regular pipeline as it is, and we're going to add data memory. And I'm sorry I'm in the way here, but the idea, I think you can see, I'm not covering too much, is that the output from the ALU is presented as input to the data memory. This is in fact the address. And then we have two things we have to be able to do with data memory. Either we load or we store. If we load, that means that we're getting data from the data memory and putting it into a register. That's the output of this data here, and then we use that as another option for our write back value. Either we're writing back the ALU value or we're writing back the data memory. But if we store, then we're taking information from the register file and putting it in memory, right? Now we need this output from the register file, and we need to carry that along with us as well, and then put that into the data memory to store. So that is the full construction of the pipeline, of the sort of the very basic pipeline CPU. And I've got a few other examples for specific implementations, one for RISC-V if you want to look at that. But that gives you an idea of the components that we need to build a machine that can do multiple things at once.